Hello, my name is Vitalii Bulygin, and I'll present our work BlitzMask, real-time instant segmentation approach for mobile devices. We are from Samsung Research and Development Institute, Ukraine. Instant segmentation is the process of identifying individual objects within an image or video frame. It can be a useful technique for analyzing drone footage, as it allows for precise identification and tracking of objects and their movement. Instant segmentation can be used to accurately identify and track other vehicles, pedestrians, and obstacles on the road, allowing self-driving cars to make better decisions and avoid collisions. In augmented reality, by segmenting the user's body part and mapping virtual item to those segments, the user can see how the item would look on them in real time. Instant segmentation can be used to identify and locate different objects in a robot's environment, allowing it to manipulate them more effectively and perform complex tasks. By using instant segmentation, mobile medical imaging applications can accurately identify and segment specific regions of interest within an image, such as tumors or abnormal tissue. This can aid in the diagnosis and treatment of various medical conditions. We were unable to find fully comparable benchmark with performance tested on regular mobile devices for instant segmentation. Why is porting an instant segmentation approach to mobile such a problem? An easy solution is to simply use an existing instant segmentation approach with light backbones, such as MobileNet, as well as low-resolution input to achieve real-time speed on mobile. Suppose we are adopting well-known solo or center mask or similar approach to mobile. Multi-ads of only mask branch is nearly 40 times heavier than the entire MobileNet V2 SSD Lite, and therefore it is impractical to use such approach on mobile. The authors of Solo V2 greatly reduced the computational complexity of the model head using dynamic convolution. Mask branch is near 10 times faster. However, this is a non-standard layer and its adaptation is currently not available for mobile. It is a complex task to produce such an adaptation. YOLACT and YOLACT++ is similar anchor-based instant segmentation approach have main problems: non-maximum suppression and resolution-specific anchor parameters at each pyramid level. YOLACT also implemented GPU-optimized fast non-maximum suppression, but is not available for mobile. It is a non-trivial task to change input resolution in YOLACT, which can dramatically decrease accuracy. For example, the authors of YOLACT reports average precision mask 29.8 for resolution 550 to 550, and every precision mask 24.9 for 400 to 400 input. Both is the same backbone ResNet 101. Our own YOLACT training for resolution 320 to 320 input size gives only average precision mask is equal to 20.1 with the same ResNet 101 backbone. The lightweight YOLACT modification named Mobile YOLACT has low input resolution 320 to 320 and is designed for mobile environments. However, the best result of the mobile YOLACT is average precision mask with intersection over union 50 is equal to 23.0, which is too low because integral average precision is usually near twice smaller than average precision mask 50. And as we show below, our approach is more than twice more accurate than mobile ULACT and has even faster speed on the same mobile device as mobile ULACT authors used. All these facts prove that using a lightweight backbone and low input resolution for ULACT approach leads to low accuracy. So what's our main idea? Our model has 4 output: heat map, coefficients, size, and spanning set. Let's tell us how we get instance mask using these outputs. Heat map has one channel for each class. Each channel of the ground truth for the heat map contains probability density-like function for bounding box center location for objects of class C. So that if a ground truth bounding box center of an object of class C is located at row Y1, column J1, then the channel number C of heatmap ground truth contains scaled Gaussian distribution with maximum value 1 at its center Y1, J1 with object size adaptive standard deviation sigma. Ground truth for the outsides contains distances from the object bounding box center of its 4 sides: width left, width height top, width right, height bottom. This box center is mass center. Then, given a Gaussian center in row I, column J, for channel C from output heat map, we can find bounding box using the size output. We express an instance mask as a linear combination of the output spanning set with corresponding coefficients. We only define ground truth for instance mask and do not require ground truth for its component used in derivations, that is spanning set and coefficients. Each matrix M with index n is a mask for a single object. We bilinearly resize derived mask M with index n to the original image size. Lastly, we define the final instance mask as consisting of pixels that are both within the bounding box B with index n, and for which sigma of M with index n is greater than 0.5. A few words about model architecture. We propose a new single-stage, anchor-free instance segmentation method. Its architecture is based on center net and feature pyramid networks. A model output consists of spanning set, coefficient, heat map, and size. The output spatial dimensions are 4 times less than the input spatial dimensions. Output size contains distances from the object bounding box centers to its 4 sides, and heat map contains Gaussian-like function for bounding box center location. We take only values on the object center from the output coefficients. Using the linear combination of them with the output spanning set, get the instance mask. We use only separable convolution with bilinear upsampling instead of combination of deformable and transpose convolution as for center net. The reason is that deformable convolution is not supported for mobile and transpose convolution has high latency on mobile device. Note that we use only well-known layers optimized for mobile devices on TF Lite, such as batch normalization, depth-wise convolution, and convolution layer. The output spatial dimension are 4 times less than input, and the channel number k is equal to 32. And we found that this selection provides the best trade-off between speed and accuracy in a series of experiments on MS-COCO dataset. The heatmap Y and sizes D outputs are compared to the corresponding ground truth using object detection loss function L box that consists of focal loss Lfoc for the output heatmap and linear combination of L1 loss and unit box loss for the output size. The focal loss Lfoc is penalty reduced pixel-wise logistic regression loss with perturbation of the first polynomial coefficient of Taylor expansion. Focal loss is used for the case of imbalance between background and foreground. Perturbation of the first polynomial coefficient has parameter epsilon1, epsilon2, and gives a near 1 mm precision compared to classic focal loss function for our best model. We define the following combination of L1 type loss and unit box loss penalize bounding box predictions. L1 loss is employed to regress size from object center to the bounding box sizes. Unit box calculate intersection over union between prediction bounding box and the ground truth bounding box. We estimate instance mask using output coefficients and spanning set using combination of sigmoid cross-entropy loss and dice loss. As mentioned before, predicted mask M with index n is expressed as linear combination of coefficients named in this formula as lambda and spanning set B. Cross-entropy is simple classification loss function which classify each pixel for each channel. In the dice loss, the denominator is the sum of total boundary boxes of both prediction and ground truth. The numerator is the sum of correctly predicted bounding pixels. Dice loss considers the loss information both locally and globally, which is critical for high accuracy. To search parameters epsilon1, epsilon2, alpha1, alpha2, beta1, beta2 of the total loss function, use fast training with backbone ResNet 18 and just brute force parameters as shown in table A until B to get one with the largest accuracy. Here we show BlitzMask output with backbone MobileNet V2 left and efficient netlight B4 right. For input resolution 320 to 320, output resolution 80 to 80. Red rectangles denote predicted bounding boxes. The corresponding object type and confidence score are shown at the top of each box. Different instance masks are shown by different colors on each image. All images have the confidence threshold at 0.3. As discussed in the related work section, there are no published results for real-time instance segmentation on smartphones with adequate accuracy, and hence table 2 sets a new benchmark for speed and accuracy on smartphones. As elaborated earlier, YALACT-H, when used with the lowest computing capabilities available in the literature, Jetson AJX Xavier, average precision max is equal 20.8 on MS Coca Val dataset with 35.7 frames per second. However, AJX Xavier cannot be used in smartphones and it's superior to Samsung S21 GPU. Further, given that YAL-H input resolution is 550 to 550, we achieve better accuracy of 21.9 with a smaller input resolution 320 to 320, but with the same backbone MobileNet V2. Our result could be compared with mobile YALACT, which achieve average precision mask 50 is equal 23.0 at speed of 21 FPS on Samsung Galaxy S20. In contrast, our accuracy for the case of efficient netlight B4 backbone is average precision mask 50 is 47.1 at the speed of 39.4 frames per second on Samsung Galaxy S21. To allow comparison with mobile YALACT, we additionally run our method on Samsung S20 and achieve 36.8 frames per second with the same accuracy as in Samsung S21. This shows that our model has twice better accuracy and 1.75 faster inference speed than mobile YALACT. As a conclusion, we can emphasize that we propose a new, fast, anchor-free instance segmentation approach BlitzMask with light hat. The new training method and loss function allows us to achieve integral average precision mask is equal to 28.9 with real-time speed on Samsung S21. And the result of the portrait mobile you can see at the right.